Okay, guys, so the recording that happened during the class period didn't work, so I made this recording on the side for you guys. For those of you who weren't here today, which is Friday. So, yesterday we kind of finished our notes off where I gave you just this function, and I asked you to rewrite it as two partial fractions. So, where we're starting today is I'm going to ask you to, if you turn the page of your notes from this example, I'm asking you to integrate that particular function. So what you're going to do, so because we already did this particular partialing out, we know from yesterday that 5x minus 3 over x squared minus 2x minus 3 is equivalent to 3 over x minus 3 plus 2 over x plus 1 dx. And so by doing this, so that work we did yesterday, again, here's proof of it here. Okay, by doing that, we were able to rewrite it in equivalent form, and now we can just use what we know about integrating with natural log to integrate this function. So some things that are worth noting, and we'll see some examples of this next week when we really start reviewing all the different integration techniques that we have, is we use this like partial fractions when we don't see an easy, like if I could do a u sub here to make this match what I have up here, okay, that would be ideal, but we don't have that u sub, so that's when, and we would also look to do this when the degree of our numerator is smaller than the degree of our denominator. If the degree of our numerator is equal to or greater than or equal to, then we might use some sort of division or separation of fractions technique. So anyway, again, we'll have a lot of examples of that next week, but I wanted to kind of point out when we use this particular strategy. So now if I was looking at, say, this one, I'm looking at this, and certainly like I know u sub seems to be working for me for this one. So what I might do is I might factor my denominator here. I'd end up with x minus 4 and x plus 3. All right, and so if my denominator was just x minus 4 or just x plus 3, I could use that natural log to do this. So what I'm going to do is I'm going to say, well, I know could I rewrite this as two fractions being added together with those two denominators? Now, one of the things that came up when I taught this to the class, so I'm going to kind of make sure we understand what's going on here, is the next thing we're going to do is try to kind of solve this equation. And so what I'm going to do is multiply every fraction by the common denominator of x minus 4x plus 3. If I do that for this one, the x minus 4's cancel, and I have a times x plus 3. If I do that for this one, the x plus 3's cancel, and I have b times x minus 4. And if I do that for this one, everything cancels, and I have 2x plus 41. And now just to do some simplifying and kind of make some sense of this, I have, I'm going to distribute. So I've got ax plus 3a plus bx minus 4b equals 2x plus 41. And so I kind of look at this at my pieces. I have my x terms, all my terms with x to the 1. And so in order for this whole equation to be true, for ax plus bx to equal 2x, a plus b would have to equal 2. And then likewise, I have 3a minus 4b are my two constants. They're going to equal 41. And from here, you can solve this system any way you want. What I'm going to do is I'm going to let a equal 2 minus b and take this a out and put that 2 minus b in its place and just bring everything else down. And like here, we're just algebraically solving the system. And then I'll subtract my 6, and this becomes negative 7b equals 35, so b equals negative 5. If I plug that in, that means a is equal to 2 minus negative 5, puts a to equal 7. Again, solving systems, you guys have been doing that for a real long time. So now what I'm doing is I'm taking this expression, and I just figured out that that expression is equivalent to a over x minus 4. Well, a was the 7 plus negative 5 over x plus 3, and then my dx. And now that it's in this form, we can use what we know about natural log. All right, so let's look at just another example. As I look at this example, and I do recognize you guys are probably just make sure to pause it as you need to keep up with the video. Okay, so as I look at this next example, now what makes this a little bit, but not a lot, a bit more complicated is we have extra factors. So the first thing to factor this is I'd pull out an x. And then I would factor that to x minus 2 and x plus 1. Again, factoring however you need to factor. Suppose if you need polysmelt, you can factor using polysmelt. I don't think you necessarily need that for this one. So now as I think through my denominators, I need 3 fractions because I have 3 factors in my denominator. All right, and I don't know what's on top of each of these. So if I multiply through by my common denominator, for that first fraction, the x would cancel. I have a times x minus 2, x plus 1. For this one, the x minus 2's cancel, and I have bx, x plus 1. Here, the x plus 1's cancel. I have cx times x minus 2. Left side, everything cancels. All right, so now as I look through it, the next thing I'm going to do is just some distributive property. I happen to know that this whole expression is x squared minus x minus 2 because I factored, like these two factors came from this. So I'm just going to distribute a to that x squared. So ax squared minus ax minus 2a. And then bx squared plus bx. And then cx squared minus 2cx. And then 3x squared plus 7x minus 2. And again, at this point, we just start matching up our like terms. So as I'm looking at my first I'm going to look at my x squared term. I have 3 coefficients, a plus b plus c. That's what's got to equal 3x squared. And then I look at my x to the first term, so I have negative ax, I've got positive bx, negative 2cx. So I've got negative a plus b minus 2c equals 7. And then I have my last term here, that negative 2a equals negative 2. And so now that I have those, I could look at those and say, is any one of these easier to solve? I certainly think this one is the easiest to solve. So when I solve that one, I've got a equals 1. And then if I plug that 1 into the other equations, and, I would then do maybe b plus c equals 2, and b minus 2c equals 8. From here, I think I'm going to do b equals 2 minus c. Just doing a little bit of work here. I now have 2 minus 3c equals 8. 3c equals 6c equals negative 2. And then b would equal 2 minus negative 2, so b equals 4. Again, solving systems, you've done systems for a long time, but you might be a little bit rusty on it. So now, what I can rewrite my expression as, let's see, a over x becomes 1 over x, plus b over x minus 2 becomes 4 over x minus 2, plus negative 2 for c over x plus 1 dx, again using my natural log function. Guys, this is a great. Okay, so for this next example, one of the things we need to recognize is, so what we have to recognize is when we have we have this x squared in the denominator, and so there's two different ways a fraction could get an x squared in the denominator. So I could just have like a over x squared plus b over x minus 2. But what happens is sometimes like that a over x squared, well, there could also be, that could be, and whenever I have a quadratic term like that, or something with an x squared on the bottom, there could also be just a fraction that's just something out of x that's being added onto that. So whenever you have multiple of the same factor, you kind of have to consider you could have that multiple of that factor and something over that, or you could have just a singular of that factor. So like if I had and just like this little side note, if I said, for instance, if I had 3 over x plus 5 over x squared, and I tried to add those together, I'd multiply by x over x, and that works out to be 3x plus 5 over x squared. And so it's possible that my original fractions that were added together to get to an x squared in the bottom, it could be I had one with an x squared and one with an x. So you just have to be a little bit conscious of that. And so as we go through to do this, we'll make this all equal to 5x squared minus 3x plus 2. So now I'm going to multiply by my common denominator. Oh, this is also over x squared, x minus 2. So by x squared, x minus 2 for each piece. And as I do this, so for that first fraction, the x squareds would cancel, and I'd have a times x minus 2. For the second fraction, the x minus 2s would cancel, and I'd have bx squared. And then for this third fraction, the x and this one of the x's of that x squared would cancel, so I'd have cx x minus 2 equals that. And then over here, of course, the whole bottom will cancel out. And I'll have 5x squared minus 3x plus 2. So now I have ax minus 2a plus bx squared plus cx squared minus 2cx equals 5x squared minus 3x plus 2. And then I just, again, start going through my pieces. So for my x squared terms, I have b plus c equals 5. For my linear terms, or my x to the first terms, I have a minus 2c equals negative 3. And lastly, for my constant, I have negative 2a equals positive 2. And then I'll just kind of go through and start solving. So here I get a equals negative 1, excuse me. here I have -1 minus 2c equals -3. And you can see we're basically just continually going back to the same kind of process at this point to solve this system. And again, now we gotta be a little bit careful as I go to so now what I'm integrating is, let's see, a over x squared is going to become -1 over x squared. B over x minus 2 will become plus 4 over x minus 2. And then c will become, c over x will become 1 over x dx. Now, it's really easy to, like the past few examples, everything's been ln x, ln x, ln x. A reminder that the integral of this term is not ln of x squared, because now I'm doing -1 x to the -2, and so I'm integrating using the power rule. I take that up by 1, so it becomes +1 over x, or because it'll become +1 over 1 x to the -1 over x. Then this one will be 4 at ln of absolute value of x minus 2, and then ln of x. And that would be my final answer. Now, for this last example in class, I'm going to show you one other thing we have to be cautious of at the beginning. And then we didn't quite finish it in class today, so I'm going to leave the very last piece to you in terms of trying to solve it. So when I look at this one, so the first thing I might try to do is factor that unfactored trinomial, and I'm looking at that, but it turns out it's not factorable. Okay, and so for similar, so we'll have we're going to have two fractions, a over x minus 2, plus, and then I've got this kind of x squared minus 2x plus 3. I do not know that the top of this fraction here, I don't know that it's a constant. It could be, I know it's a degree smaller, so it could be a line on top of this. So when my bottom is quadratic, it's possible to have bx plus c on the numerator. So when my it's always that the numerator is going to be 1 degree less than the denominator. So when it's x to the first, a constant is what goes on top. But if my denominator is x squared, so a second degree polynomial, my numerator could be x, a line of ax plus b or whatever, or in this case bx plus c. All right, so now, and then we'll have this whole thing again equal to our typical set, what we're trying to integrate in the first place. So now, again, technically we're multiplying through by the denominator to everything. If you get to the point where you just want to be like, you're multiplying by what you need to multiply by, it is absolutely fine. So I'm just going to kind of write what we got here. So now I have my numerator bx plus c is going to, so now I'm going to have a little bit of extra distributing and stuff I got to do. Okay. So then, again, I'm just going to keep doing my little distributive gig here. And then we do the bx squared minus 2bx, and then I distribute that c. And I know that you guys are probably, feel free to pause this video. The video is much shorter. It took the whole class period to do these examples today. And I think this video is going to end up being 20 minutes, so, you know, I probably should have told you that at the beginning. There we go. All right. So my x squared terms, and I lost my squared here. My x squared terms, I have a plus b equals 7. And then my next one, -2a, -2b, and c. And then 3a minus 2c. And then I think what I would do probably is make a equal to 7 minus b. So now I have negative 2 times 7 minus b minus 2b plus c equals negative 13. And let's just do some simplifying here. Negative 14 plus 2b minus 2b. Oh, that's lovely. So those cancel out. I have negative 14 plus c equals negative 13. I'm going to add 14. And now have c equals 1. If I know that c is equal to 1, I can say 3a minus 2 times that 1 equals 13. 3a equals 15. Again, if you just want to jump to these at this point, it's fine. If not, pause the video and kind of work through them. It's not a problem. And then I have a equals, I'm sorry, 5 equals 7 minus b, so b would equal 2. All right, so now let's separate this out and think through kind of what this means in terms of what I'm integrating. I'm rewriting now my integral as, let's see, I have a over x minus 2, so that'll be 5 over x minus 2, plus this bx plus c means I will have 2x plus 1 over x squared minus 2x plus 3 dx. All right, so this is kind of where I cut things off in class today. We did kind of do like, all right, I'm going to integrate the first one. I get 5 ln x minus 2. And then I kind of left it as, you guys go ahead and try to do this, the second part of this integral. And my intent in giving you this particular example is that this example comes with a little bit of, it's not easy. You're going to be, while the skills in this we actually did in 1151, and we did a little bit this year, there's some tricks to this. So I want you to try to do it on your own. We're going to talk about it some more on Monday, but this particular one comes with a whole bunch of complexity and nuance, and it has a good array of different strategies beyond just separating by partial fractions. So give it a shot. Try not to use ChatGPT or anything, because I want to see if you can figure it out on your own. And like I said, I'll show you guys how to do it on Monday if no one figures it out. So talk to you guys soon. Bye.